So, topic of this talk is standard allocators in C++11 and now C++14. For those of you who don't know me, I'm Alisdair Meredith. I currently work for Bloomberg in New York, and I'm the current working group chair for the library working group. And was indeed in that role as we voted this into the standard, but was not at the point that this was actually adopted as part of our working paper. So I decry responsibility there. But I think we made good progress here, and hopefully that's what you've all come to hear about. So out of curiosity, who has explored using allocators prior to C++11? That's a good show of hands. Who had success exploring allocators prior to C++11? Far fewer hands, and a lot of them are a bit wavy. So hopefully you're going to see that what we've done now will give you success on those experiments you were trying earlier. I'm actually happy to see some of your hands went up. It's normally been a dark corner that most people have just said, allocators, we don't do that. So I've got a good audience today. Traditional copyright notice. This is copyright Bloomberg, but hopefully we'll have the slides distributed after the session anyway. Topics to cover. Some motivation about why we want to explore the allocator space in the first place, and then a worked example or two just how we might be able to do so. Then we'll dive into the problems that arose back in C++03 in the original 98 standard, where allocators were part of the system, but in many ways didn't quite work. And then the solution we came up with for C++11 that generalized the model and notion of allocators. And then we're going to look at some examples of how we actually can use that in practice. Just a quick warning about the slides that are coming up. My traditional sessions I give tend to be in breadth rather than in depth, so I tend to talk fairly quickly because I'm covering some broad material. This is me trying to go the other way where it's much more in depth than breadth. So if I'm going too fast, slow me down. Somebody raise up and say, oh, we just need to catch up with you. I've presented this kind of material a few times in the past, and the general response is, that would have been a great 3-hour session you crammed into 90 minutes. It all made sense, but as soon as I blinked, I could never catch up. So slow me down if I go too fast. I've got fewer slides this time, so I might get to the end and find we have time to spare, but I wanted 90 minutes, so they gave me 2 hours because there was no 90-minute session, so hopefully this will pace about right, but we'll find out. So we'll start with a basic question to orient ourselves. What is an allocator? Definition I'm going to go with is allocator is basically it's a mechanism that's going to supply memory on demand. Typical use case we're having for an allocator is it's going to be an implementation detail for any kind of object that needs to allocate and manage some kind of dynamic storage and state. And typically those tend to be containers. Not always, but even though we'll typically view something that uses or acts like a container as if it were a container, something managing memory is going to want some way to control that. And I'm going to give that an additional goal. This was key to what we were doing at Bloomberg, that we want to be able to control this down at the per object level. Because when you're writing code and you're creating your objects and you're trying to manage your memory, you're managing memory for that specific object. And at the time you're creating that object, knowing the lifetime of that object and what that object's going to do, you have far more information than some abstract library author trying to write a general purpose allocator for all things that's great for all times for all men everywhere. So you want to be able to bring context to bear on your specific object and say, this object maybe has a different allocator to that other object because I can do something much more specific here and take advantage of my knowledge. But on the other hand, we don't want to complicate the whole system everywhere, so everyone is now worrying about every time they create an object, what kind of allocator do I give it? The default should just work, and it should be that reasonable all-purpose, general-purpose allocator that gives a good answer the vast majority of the time, which is essentially the allocator we're using in C++ in C++98. So if you have nothing to add, don't say anything, and you get a good default. We don't want to make life hard. So this is our other goal when we're approaching the space of allocators and where we were back in 98 to say, how can we move forward and have something more useful? So I came up with a few motivating examples for what kinds of things might I want to do with allocators. A classic example is thread-specific allocators. I know that I've got an object who's only going to be accessed from within a single specific thread, but every time I go to memory, if I'm going through global new, That's a shared resource across the whole system, and there's some kind of synchronization will be happening under the covers, so I can speed up just by eliminating all that synchronization, managing just within a given single thread. Which is what I say, context. I know my object's going to be accessed only within a single thread. I now might switch to using a thread-specific allocator. Classic example of a thread-specific allocator is I'll just make myself some space on the stack and allocate out of that, because only my thread has access to that part of the stack anyway. So that's a very simple thread-based allocator. Pooled allocators are another fairly common notion where I'm going to keep recycling and reusing the same memory over and over. And I don't want that fragmenting throughout the whole system, so we'll manage some kind of simpler set of pools. The very common one that I end up using in Bloomberg most, because I write lots of code, I end up writing lots of test drivers, and the test drivers want to make sure that my code is using memory correctly. I end up using a lot of test allocators and diagnostic allocators that are just instrumenting how my specific objects are using memory. And again, this is very good to be down at the per object level, so that different objects, even of the same type, I want to check which one leaks if there's a bug in my code that my test driver is exposing. So testing allocators are a very useful resource for us at Bloomberg. And my final example will be shared memory allocators. This is another common request. Can we somehow support allocators for objects in shared memory that might even be able to use across multiple processes with that shared memory mapped into different points in the address space? So these are ideas we have in our mind as we're thinking, how can we better specify the allocator concept for C++11? I'll just walk through a quick example. One of those I mentioned earlier was the idea of allocating off the stack. At Bloomberg, we call this the buffered sequential allocator. So the idea is basically we're going to allocate memory from a buffer you supply to the allocator itself, which will typically be, I've just created an array of 1,000 char, 2,000 char or something, because it's going to be a reasonably small allocation on the stack. If I exhaust that amount of memory, I will then actually fall back on a secondary allocator that says, okay, you exhausted the small pool you gave me, give me another one, but we'll go to that secondary allocator much more infrequently because it keeps giving us larger and larger chunks, just to make sure that our allocation remains is efficiently coming out of these large sequential chunks of memory. Typically, in our case, that just goes back to an allocator that uses new and delete, just kind of a global resource. So maybe a slight synchronization at that point, but the goal is never to hit that second allocator. And the other thing that this allocator does is the allocation is a no operation. We're never going to try and reclaim that memory. We're not going to try to sub-allocate and track the use here. It's a very specific use case that we call sequential allocation. We just consume the resource you gave us, and then we're done. So this is my proposal for a reasonably simple allocator that might be fairly efficient. See who's been paying attention. What efficiencies are we expecting to gain with this kind of a design? You stay quiet. Okay, so can we go ahead? I'm hearing a lot of good answers bubbling up. Just call a couple of hands. So go hand in the middle here.
Cache localization.
Okay, good cache localization, cache coherency. Any other suggestions why this is a good idea?
You mentioned earlier there's no lock on the CRT that's across the entire stack.
Yep, because this is all coming off the stack, there's no synchronization involved, so be good threading benefits. Any other benefits here? No garbage collection. Because the allocation doesn't track this, that's fairly cheap, yes. The implementation suggestion is the implementation is very efficient just because the computations involved are so simple. Okay.
It's constant time, you just advance the pointer of the increment or something. It's a very simple path.
Sorry, could you repeat that? I got to silently ask at the back saying ask me to repeat the question, but I'm repeating answers to the question I gave at the start of why is this an efficient allocator. Sorry, what was your answer again?
It's simple and fast, constant time.
Constant time. Essentially constant time, because all we're doing is advancing a pointer apart from that rare case where we go back and default onto a final allocation. One other answer at the back.
When you return above the scope where you observe that space, you drop all the objects in that space until the building can go.
Okay, so because we're not doing any bookkeeping, the deallocation is very quick and simple. We just leave the whole buffer aside in one hit. Again, very fast. There's one advantage of those that I also listed was low memory fragmentation. Because this is coming off the stack, we're not fragmenting the global heap. So in a long-running system, this is again going to pay off. The reason I put locality of reference kind of in brackets, we do get that property here, but on most allocators you implement, you actually find that you tend to, locality of reference is almost a natural property that comes out when you start working in this space. But this does give that in space because you are very, very local, actually being in the cache lines of the current stack itself. So these are all the great things for why you might want to use this kind of an allocator. Why wouldn't you use this allocator? It's not a silver bullet. So the next question is, who spots some risks with this? At the front. Stack corruption. Is there a real risk of stack corruption with this design?
If it's recursive, you may run out of stacks.
Okay, this is a problem. If I recurse a function that's using this kind of an allocator and I'm allocating my code on the stack, there's a problem. But remember I said if I couldn't satisfy the request, I'd go out to a second allocator to allocate another array on the heap.
The higher level system could have a bug, and that bug could lead to stack corruption.
Well, bugs outside my code causing stack corruption are not, I'm going to put bugs I don't know about outside the scheme of things. But I will buy a recursive call through this kind of code. Or,
Allocator drop and written for debug.
and there is the problem that, yes, stack space isn't free, that if I do just try and grab some memory, I allocate a large array on the stack, the failure mode when the system can't honor that tends to be very, very subtle and unpleasant to try and track. So I'll go at the back and then at the front here again.
If new people to the system don't understand the lifetime management and they pass that pointer off to another process, you are in for a large amount of trouble because of corruption that might occur.
So again, just going to repeat the answer. The problem is if this object that's got its allocator on the stack somehow escapes that function scope, I've now got an object using an allocator, so some crazy dead stack space that might get filled in by other things, who knows, but it's a very pernicious kind of bug. So we want to make sure we don't do that. Any other concerns? That was the one. Okay, at the back again.
Inconsistent speed, because you said that there is a chance when you reach the end that you're going to allocate from the heap, and suddenly that allocation is much slower than all the other allocations.
So if I'm relying the answer is if I'm relying on those speed characteristics, I said it's very efficient because all I'm doing is a simple pointer addition. So I'm in a hard real-time system, for example. The fact that very occasionally, if we miscomputed our original buffer or we're relying on the overflow behavior, the occasional allocation becomes expensive, creating a second overflow buffer. That might actually be sufficient to discount wanting to use this in the first place. So yes, we have to be aware of that. Any other hands? I'll take one more.
No deallocation.
The lack of deallocation, why would that be a problem?
Because you can't use that memory again. You're eventually going to run out.
So because we're not releasing the memory, if we're in a cycle that keeps trying to consume memory, yes, and that's going to become a problem because it's going to go to the overflow and keep allocating more and more, and that's not going back to the system. Yes, it does catch us up reasonably quickly if we've not anticipated that kind of a design. I see one more hand, then I'm going to go to the slide.
Alignment, you must manage to correctly alignment when you take that.
So, prompt at the front about alignment. We'll come back to alignment later in general. Last hand at the back.
And there's no buffer overflow protection. If I have a bug in my code that overflows the stack buffer, unless I overflow the entire thing, I don't know.
Well, if I have a bug that overflows the memory allocation that the allocator supplied, I have a problem. But I don't think that's a particular risk to this allocator, because that's a bug that you weren't using the allocator, whichever allocator your system has correctly. You've got a bug that you're using memory that you weren't given.
You have no way to detect it, though.
So we don't have a hyper-secure allocator that's trying to track those additional allocations. I find that hard to describe that as a risk of this allocator as opposed to if I've got a help me find bugs in my code allocator where it's a specific virtue, I have enabled that additional checking. But again, that's a matter of perspective. I'm seeing one last hand very eagerly going up. I want to keep moving. But.
Just very quickly, there's more danger if you overwrite the heap, then you may be overwriting areas you're not using, but if you're overwriting the stack, it allows an attack vector to come in.
Okay. Again, for the camera, that was a very good point, that if we do have a bug, the program we're dealing with is buggy, but the risk that comes from the bug is that overwrites of the memory that we returned are actually overwrites of the stack now rather than overwrites of the heap. And the very act of that bug overwriting the stack is a much more dangerous kind of bug to expose to our clients. In particular, it's a very popular security exploit. Yes, thank you. That's a good clarification. I had most of those. The one I was waiting to hear right at the top was this is not thread safe. We chose it because it's not thread safe, but we need to be aware that if we try and share the objects using this allocator in multiple threads, our allocation behavior itself will not be thread safe. So don't use this allocator where that is a concern. And again, the notion, I think, with the idea of saying, this, because we never deallocate, if we've got a use case that's lots of allocate release cycles, such as I'm pushing into a vector and the vector then has to move its elements and grow to expand, that tends to be a problem. So hence, poor match for containers that resize in regular use. I'm thinking particularly of vector and string here. So key usage is when the upper band of memory that you expect to use is known. This becomes a very useful allocator to back unless you're in this rapid churn kind of a scenario. So some use cases I suggested for this is basically you've got a short duration container composed within a function of a reasonably well-known capacity, or you're doing something like building a string, caching some computed values in the middle of a larger computation, or building a dictionary of a known size you're going to use for lots of lookups within a function. Typical use case for this kind of an allocator, but there are many allocators. This is one point in the space, but I'm just trying to give us a motivation to have something in mind as we're looking at some of the other material. So I have an example of how this might actually be used in practice. This is an example using syntax we have from the Library Fundamentals TS that's currently out in Ballot. In there we've got an additional allocator facility called Polymorphic allocators that kind of let you supply the allocator at runtime. So this is how we might build something like the sequential allocator I just spoke about using the new proposed standard facility. First thing is we're going to create something called a monotonic memory resource called alloc, because this is going to serve as our allocator. We pass it a character buffer of the appropriate size that we're going to use. The size we compute as being, we're going to have 3 vectors with 100 doubles in each, so we compute it as 3 times size of a double using the CppCon2014 new type enum, so I can tell the enum that it's got an underlying size t. That's mostly just being cute, showing the CppCon2014 syntax. So I have a question coming up at the back.
Would, just semantically, would the array container also work and be more aligned with CppCon2014?
So could I use the array container here rather than trying to create vectors of specific size? It depends upon what my usage is. Because an array doesn't initialize the doubles, it could just work, but I'm then tracking the capacity. There's no pushback insert and these other operations. So, and if it was, say, something that was either not default constructible as the element type, or it had, or the default, default constructor was maybe expensive, I would still rather have something where I'm dynamically growing and managing the size. But yes, array is something to still bear back in mind, that if you've got a fixed capacity, you're going to fill that 100, it's always going to be 100, the array is actually a better abstraction for what you're doing. So the intent is I'm expecting the size of these things to vary depending upon what might happen at the work that happens at the end. So the enum size t is basically just showing off some CppCon2014 syntax in case people haven't seen that. The other thing I'm doing with CppCon2014 is because I'm going to be storing doubles in my vectors, I want to make sure that the character buffer itself is aligned as a double. So that will be aligned as a double on the stack. Finally, I now pass this my allocator to my vectors. You'll notice that I've highlighted everything here is in namespace PMR. That's effectively std PMR within the new the new fundamentals TS. We'll have some slides talking about the use of namespace here at the end. But the main thing, just to explain here, is this means the vector you're looking at is standard vector, but PMR just has an alias to standard vector that uses a slightly different kind of allocator. So vector as you know it with just another allocator substituted. In the polymorphic model, where the allocator is supplied at runtime, we actually pass the address of the allocator, so we're passing in by pointer rather than by value. And just because we want to make sure that vector has this really nasty doubling property when you start using it, we want to say up front, I'm expected to hold up to 100 elements. We're going to reserve that space now, so we're not doing lots of additional allocations throughout the function, just consuming from our buffer here. So after all this is done, finally we can go off and do some work. Does anyone see any issues with this? I see a hand at the back.
Alisdair, why pass in the allocator instance by pointer rather than by reference?
To make it clear is coding convention. We use that a lot at Bloomberg. We thought it was the right thing to be proposing here still for the standard. We want it to be clear that we're doing something dynamic. We prefer to pass by pointer rather than by reference first, because we're going to store a pointer internally. We're not going. So why do we want to make the code inside take the address, whereas we can just have pointers all the way through the system? The way you pass these around, pointer is your vocabulary type.
So what is null pointer as an argument?
Good question. What we do in the case of a null pointer is we have a system global default allocator that is what you will use unless you supply an allocator. And that's what our internal Bloomberg code falls back on. I can't remember if that is exactly what we do in the standard form as well. I'd have to go back and double check. Question?
The vectors, will they on construction allocate some memory?
There's always the potential that the initial construction passing the allocator could allocate some memory. This is a good risk to be, and therefore we're not, although we made a buffer just for 300, we might have more than 300 doubles being consumed here. That's a good risk to be aware of. I'm not aware of any implementation that does that, but generally implementations of quality will try not to do that. They prefer their default constructed containers to have no allocations, but it's something to be aware of. The other issue to be aware of is reserve isn't guaranteed to give you only 100 elements worth of memory. Typically, if a container is thinking in terms of, I'm just going to go to a power of 2 and keep doubling, is a popular idiom here. And there's other idioms for reserve. But they might overcommit just because you said, I want space for at least 100. So it's possible that by the time you get to that last reserve, that's already having to hit the other secondary allocator to bring some more memory in. So these are just ideas to be aware about. Read your library documentation to find out, or explore with the implementation to see if its reserve behavior is like this. For our own implementation that we use at Bloomberg, we specifically made sure the reserve implementation does exactly this because we know we have this kind of a use scenario in our code. There was a question at the front.
I guess I'm still not clear why you need a line as double, and it seems that this particular instance of allocator can only be used for vector doubles.
Okay, so the question was, we don't see the need for the align as double here. Well, the issue is I'm just creating a character array. So the character array is going to align however the system wants to allow it to align. But I know the elements I'm going to store in my vector are doubles. So I want to make sure that the buffer that I'm storing them in has the same alignment properties as the elements I'm going to store. Otherwise, I'm going to risk having misaligned elements handed out.
It's when you call the allocator, you must give the alignment to the allocator.
And the suggestion is when I call the allocator, I should give the alignment to the allocator. And to an extent, I'm watching some of these details, scrolling past some of these details. The way that, I say this is mostly modeled on the Bloomberg model. In the Bloomberg code, we currently assume that all allocators have to return maximally aligned memory. And we make it a requirement that when you pass us in a pointer, it's a pointer to maximally aligned memory. The standard system actually does, that this modeling is this proposal is modeling, does allow much more fine-grained control over the alignment. So it becomes much more important that we actually get the alignment right up front, because unless we use explicit syntax to handle all the alignment, it's then going to be, we have the misaligned issue. And it also means in this case that if the alignment's being managed by the allocator under the covers to say, give me something of the appropriate alignment, and that buffer wasn't correctly aligned, we're not going to get 300 doubles out of it again, because we're only going to get 299, for example, because the alignment will have cost us something. So if we know we're going to be creating elements of a certain alignment or with a certain alignment requirement, it certainly helps to make sure that your buffer that you're supplying has that same alignment property. And that's very easy to do in C++11. It was much trickier prior to C++11. Another question in the middle here.
Yeah, why are you doing character buffer and then aligning as double? Why don't you just do a double array?
So the question is, why am I creating a character buffer and aligning it rather than creating an array of doubles in the first place? Well, I'm just trying to give a simple slide as an example. So I chose double as something I could easily work with. If that was string, and I created a string array, suddenly I'm running lots of default constructors that I don't want to be running. In general, the allocators traffic in raw memory, and character arrays are C++ syntax for raw memory. There's wording in the standard that says I can treat any piece of memory as if as a character array, address it with a character pointer or an unsigned character pointer, but not any other kind. So character buffers are special in this regard. And I chose character rather than unsigned character just because it was shorter to type. Any other questions before I move on? Okay, and now I have, yes, I just walked through all that. So that's the basic background of my motivation, and a quick example of what this might look like being used in practice. So from there we go on to how does this apply for the standard as we had it in C++ 2003, or otherwise known to me as the reason why Bloomberg joined the ISO committee in the first place. This was prior to my actual joining of Bloomberg as well, but we have in the front row the poor gentleman who had to propose this and get this through the standards process. Thank you, Pablo. And as I say, I think it's a fantastic piece of work coming out the far side of it, but it was quite a journey. One of the other motivations we had at Bloomberg coming into this area, we had a very specific allocator model in mind. And the key for us is what we call vocabulary types. Vocabulary types are the types you use in your interface. And the big benefit from vocabulary types comes from having very few of them. The fewer vocabulary types you have to express the same idea, the much more interoperable all your software becomes. So we have the idea we want to have a small number of vocabulary types, but we also want to have a rich support for allocators. And when we come to C++03, the allocator is now bound in as part of the type of your class, of your container, which means that something like you want standard string to be your vocabulary type, but string with allocator A and string with allocator B are different types and not necessarily compatible with each other. So this is the problem we wanted to solve. So to an extent, I showed you our proposed solution on the previous slides, is the idea that we can pick the allocator at runtime, you turn it into a more traditional virtual functions and dynamic dispatch, but you still need to have an allocator that wraps that. Our initial proposal, in fact, to the standards committee was throw away all your existing containers and do some new containers that just do things our wonderful way. Yeah, that didn't fly. But the other idea then was, okay, we've got these vestigial allocators that some of you have experimented and tried using them, not necessarily with a great deal of success. There was clearly an intent to support allocators in the system, but the standard didn't work for a variety of reasons. So could we come to the C++ model that was there in 2003 and generalize and fix that model so it would work and allow us to plug our model in as one of potentially many different models that people chose to implement? So our goal at this point is simply to fix the allocator model in C++ 2003 and not yet plug in the Bloomberg allocator model itself. I'll keep referring to that because it's the example I'm most familiar with. But when you're reading these slides, don't think this is all just to make the Bloomberg model work. What we're doing is we're generalizing the notion of allocators so that they will support a wide variety of different models. With different models, you're going to have more vocabulary issues, but within a given domain, you pick your vocabulary, you pick your allocator model, and everything should just work. So key issues are, the allocator is now part of the type, but it was too late for us to fix that. That ship had sailed. So we could try and mitigate this, as I say, by using the allocator support that was in C++ 2003. But there was wording in the standard that specifically allows the implementers to ignore the allocator you're supplying effectively. And there was a second piece of feedback we got from the committee that even making simple allocators around what people were trying to deduce to be the system in 03 was too complex. So if we're going to open Pandora's box and work with allocators, could we please solve both of these problems to make it worth addressing the problem in the first place? So what are the weasel words in the standard that say we couldn't actually do what we wanted to do by default? we've got these two wonderful phrases. All instances of a given allocator type are always required to be interchangeable and always compare equal to each other. This is important because if two allocators compare the same, that's implying that memory allocated from one can be deallocated by the other. But if all allocators of the same type compare equal, it means you can't actually have any state in your allocator that controls allocation behavior, which is really unfortunate when we want to store a pointer in there to say, here's the pointer to where I'm actually going to dynamically dispatch my memory to. We desperately needed state in our allocators. There's this so we need to lose this wording. So, translation. Objects cannot have state that affect actually allocation behavior. You might still have some instrumenting, how many times have I been called instrumentation? That might work. But in terms of controlling the allocation behavior, all bets were off. Then we have this other piece of weasel wording that says, the type def members in your allocator can be assumed to be T star and T const star for pointer and pointer to and const pointer, and size T and put a diff T for the size type and pointer difference type respectively. So the translation of this is, you can't have allocators that return any kind of fancy pointer, became our term of art here. And this is the kind of problem you run into if you're trying to do inter-process shared memory allocators, where you're not going to return a raw pointer because that raw pointer doesn't mean anything in a different process trying to use the same block of shared memory. You have to create some kind of fancy pointer that is an offset pointer, typical smart pointer kind of idiom. And that's what your allocator needs to return. So this wasn't as valuable to us for what we were doing for the Bloomberg model, but it was vital for solving the general case purpose of removing the weasel wording and generalizing the allocator model. So we could just wave our magic wand and say, these words are gone. And now it's up to all your library vendors to figure out how to work with these systems. But again, we also wanted to make allocators themselves easier to write and not have people compelled to write all this verbiage everywhere. Kind of like we get a similar benefit with iterators from iterator traits, which oddly enough was the inspiration for a solution that we call allocator traits. So the idea in the C++11 model now is allocator traits describe all the customizable properties of your allocator. And to make writing allocators really simple, they provide good defaults unless you choose to customize. So the majority of things we might want from an allocator can be deduced through allocator traits for the vast majority of things the allocator is going to do. Which means that every time a container wants to use an allocator, it should not go to the allocator itself directly. It should perform all its allocation behavior going through the allocator traits with the allocator. Because that way the traits can supply the defaults that the allocator itself says, yeah, just do the same sensible normal thing. So what does that look like? We've got about 3 or 4 slides of the interface now for allocator traits. First of all, we have some standard type aliases that are very useful. Allocator traits, it's templatized on whatever kind of allocator you're dealing with. So the first type def is just so you can get back which allocator did you give me. Then we have value type, because allocators in C++ are allocators for objects rather than just supplying raw memory, which you might have noticed was what the Bloomberg model was doing. We need to return, I'm an allocator for ints, I'm an allocator for doubles, I'm an allocator for strings. So we need to know what kind of things your allocator allocates. So all allocators have to have a nested value type. This is not optional. That's how we know what the allocator is allocating for. Then we have a variety of, again, useful type defs that containers and people consuming the allocator will need to know. What kind of pointer or fancy pointer does the allocator return? What does it look like if I've got a pointer to const elements rather than the non-const elements? Sometimes we need to get a void pointer out of that as well. So we've got the type def for void pointer and const void pointer. Size type, difference type. What if I subtract two pointer values? What type am I going to get coming back out? So these are all important properties. And that C below wording we're going to look at later is, I can give you a good answer for this if this type def is not found in your allocator. So the default answer is, it's the allocator : pointer, const pointer, void pointer type. But if you haven't given me that, I've got a formula to give a good default. So in the case of pointer, I know value type, so it's value type star. Const pointer is const value type star. Void pointer is void star. Or maybe, depends on whether or not I've actually figured out what pointer might be. So if pointer was supplied and isn't value type star, I actually need to have a void type of whatever that pointer type was, which starts getting a bit interesting for your library implementer, which is why all this craziness is down in allocator traits, and mostly you don't have to worry about it. In about half a dozen slides, we're going to worry about it. Next set of aliases that are useful. If I've got an allocator for my element type, I might want to actually be allocating something slightly different. For example, if I'm implementing standard map, I'm going to be storing my elements in nodes, so I allocate nodes, not the element that you gave me. So I need to now have, you gave me an allocator for, well, let's say set rather than map. You gave me an allocator for double, but I now need to allocate node of double. I now need the allocator for node of double. So rebind alloc will give me the alias for that allocator rebound to doubles. And again, I will frequently want the allocator traits for that type, so I can easily get that as well using a C++11 alias template. And the C below is, again, this is copy-pasted straight out of the standard. This is how you will go and figure it out. If my underlying allocator has the rebind alloc property, alias template, great, it's just that. Otherwise, here's a formula to try to figure out. You gave me a template, maybe I can figure out what the type parameter was, and with suitably crazy template metaprogramming, deduce the appropriate rebound allocator for you. We're going to do that. Allocator propagation is something that, if you've not played around with allocators, you've probably not had to think about. If you've played around with stateless allocators, like standard allocator, you probably still didn't think about this issue. But once your allocators have state, you get some interesting questions. So in terms of the Bloomberg model, the allocator is bound to your container at the time that you allocate it, at the time that you construct it. And actually, I find this works getting my model around the non-propagating allocator model. It seems to surprise people that allocators might not propagate. If I think in terms of the shared memory allocators, if I'm storing my object in shared memory, I'm going to want, first of all, I've got an allocator saying I'm storing my object in shared memory. All the pointers in my data in that container have to be the fancy pointer into shared memory. And likewise, any elements that I store in there are also going to be allocating in shared memory. So a shared memory vector of shared memory strings needs to make sure these allocators are coupled throughout the whole lifetime of those objects. So if I've got a shared memory vector of shared memory strings and another shared memory of more shared memory strings, but they're in different shared memory segments, and I start trying to swap elements between the two, I need to swap the characters in the strings, but I really don't want to swap the allocators that they're using, because it's a real property that the allocator of the elements in the container has to be the same as the allocator of the container for the whole duration of these allocators in their shared memory segments. So we get this world where allocators generally don't always want to propagate. But there was also a strong familiarity with people who liked the idea that if we hadn't thought about this, we just naively always swapped and assigned our allocators when we moved elements around. And especially when you think in terms of something like a move construction, the whole point of the move construction is to efficiently move that memory across, and that would take the allocator with it. So the end result, we have some fine-grained traits that are, again, part of the allocator traits, with nice short names like propagate on container copy assignment. So when you're doing a copy assignment of your container, you query the allocator traits to say, should I be propagating the allocator through this assignment or not? And similarly for the move assignment, and similarly for the swap. And in hindsight, I think this is something where we were just being a bit conservative in where we specified the standard. We've made this very fine-grained so that people could customize the wide variety of behaviors they were imagining. We didn't have much experience with this. We knew there was the model where allocators always propagate, and the model where allocators never propagate. But rather than bake down this as just a binary choice, we bought ourselves some freedom for the future by making this more fine-grained and composable. And in practice, I think this is going to be buying us some problems. I don't want to live in a world where I've got an allocator that propagates on swap but not move assignment, or vice versa. Those really feel like they should be coupled in one trait for me. And at that point, I'm not sure I really want any of this fine-grained. I can see one trait working here, but we have 3, and we have to deal with it. So I saw some hands going up.
What are the defaults?
So what are the defaults? The defaults are the allocators do not propagate. Because those, when we were working the model that we're familiar with allocators, our working model was allocators not propagating was what worked well for us. In the case of a stateless allocator, it's really not going to matter.
It also didn't propagate in C++03.
Hmm?
We were also consistent with C++03.
C++03 said nothing about propagation, whether they would propagate or not, because they didn't care. They were all going to be the same.
It said it could be the same.
Yeah. But the notion of propagation, the question never arose because people were thinking only of stateless allocators. They weren't aware there was a question to even think of. It's only when your allocators have state you're confronted and you really have to have an answer for this. So. And finally, we come down to the actual member functions of the allocator traits, because I actually do want to be able to allocate memory very occasionally with my allocator. So what we have are a lot of static member functions. And you'll notice that the first argument to each of these member functions is an allocator. So the idea is I've got my traits, and I'm going to say, trait, here's an allocator, go and do one of these things. And the interesting thing you'll notice is sometimes we're trafficking in the pointer type, and a couple of these methods we actually do drop all the way back down to being a raw pointer. But let's quickly walk through the methods. Allocate clearly says, give me some memory and give me back a pointer to whatever kind of pointer you're using for the memory you allocated. And I'll tell you how many objects worth of memory I need allocating. This is fairly similar to the C++03 interface. Deallocate, likewise, says, you gave me this pointer, have that pointer back, and this is how many objects I requested when you gave me that pointer. Construct and destroy are interesting customization points. Typically, when you're thinking, I just want to construct, you've given me back the pointer, I'm going to do an in-place new of that element, and I can now, C++11, perfectly forward that parameter pack of arguments. But sometimes allocators want to do something interesting here. I might want to store a bookkeeping cookie before or after the object, so I can then query that when I'm doing subsequent allocator operations and doing various sanity checks. The example I spoke about earlier with the shared memory allocator, where I want to make sure all the elements in that vector have the same allocator as the vector, means I'm going to interpose on the construct of the element to pass an allocator to the element in addition to the arguments that you gave me. So construct and destroy actually become interesting customization points in C++11. What's my next slide? So, yeah. But again, you'll notice construct and destroy. These are trafficking in raw pointers, because at this point, I'm constructing and destroying a specific object in memory. So I need a real address to say that's the object I'm constructing and destroying. And we've templatized as to what the element is, just because that turned out to be much more useful in practice, where I've got an allocator for nodes, but I'm trying to construct the element. Because it turned out one of the rules is when I call construct, I'm constructing the element that the user requested I construct. I'm not constructing the whole node. So if I'm using some kind of node-based containers, I need to allocate nodes and initialize my pointers tracking my trees or my lists. But I only call the allocator construct to construct the element stored in the node. So that's a subtle point that's worth calling out. And that's why these are generalized, just because I might have the allocator for the nodes, but I want to construct the elements. And it was easier, rather than making us jump backwards and forwards through the different allocator types, just to handle those. Yes, question?
This may be too subtle for me. What's the difference then between pointer and t-star? Does pointer have to be implicitly convertible to t-star, or is that conversion sort of a property of the container itself?
Okay. So the question is, what is the difference between pointer and t-star? Other than the fact that pointer is pointer of the allocator type and t-star is deduced as anything. No. The pointer here is if I've got an allocator for shared memory, it's passing me back a pointer to some amount of shared memory. Whereas this t-star is really a native pointer within the language that is the address of that object in this address space.
But I mean, when my container is going to call allocate, right, to get some memory, and it's going to get back one of these magic shared pointers.
Correct.
But then it has to construct the elements, so it needs to somehow convert this pointer
Yes,
Who knows
it
how
does.
to do that?
You will see the slides later on.
Okay.
Question?
If there is no construct or destroy,
Mm-hmm.
will be able to achieve the same effect with just allocate and placement?
That is our default behavior. So the question is, if we didn't have construct and destroy, could we get the same effect just calling placement new and the in-place destructor? That is what these will do by default if the allocator has not provided methods with this same name that perform that customization. But if your allocator wants to customize the behavior of constructing and destroying elements, this is its customization point that it can inject some different behavior there. So if your container chooses not to use these and just do the in-place new and destroy itself, it's costing the allocator its customization point. And the allocator could be relying on that. That could be part of its logic to say, when I do deallocate, I'm going to check and say the cookie I wrote there when you called construct says I came from this allocator. So it really is important that you use these methods through the traits that will figure out the dispatch for you whether or not your allocator has actually supplied these customization points. You supply the points by simply implementing these functions. So construct and destroy are optional functions of your allocator, but they will be used through the allocator traits if you have supplied them. Allocate and deallocate, those are vital vocabulary. These are what allocators do. You have no choice. You do have to supply those two functions. And finally, we have max size. It just gives you an indication of this is, in the ideal world, the largest number of objects I could possibly allocate. It's not a guarantee that I can ever allocate that number. So again, typically by default, we will just say you've given us a size type. We know the size of your object. We know, therefore, we can figure out through numeric limits, maximum number of objects divided by your size. But if you want to provide something more precise, we'll find it. So again, size type and this funky new function, select on container copy construction, are both optional functions where we provide the default. In the case of this funky last sounding function, we just provide you, we copy back the argument that you supply. The reason this is a customization point is when I was talking earlier from the Bloomberg model, if you don't give us an allocator, we want to use the default that is our global system-wide default. And that applies to copy construction as well. So when we're copying a container, where do we get the allocator from? The obvious choice we've said here is, oh, I'll copy the allocator that you gave me. But an alternative choice could be, I can, in our case, we say we've got a default allocator we use in the system at large, which is important if this allocator is a special purpose allocator, pulling memory from the stack and say I'm trying to do a return value or copy my allocator out somewhere else. I don't want to accidentally make a copy of a special purpose allocator that's using a much more constrained resource. So the default behavior is copy the allocator. There's no notion of a default allocator in the C++ standard. But this turns out to be a very useful customization point for certain kinds of allocator models. So we discovered it, we made sure it was supported in a standard model as well. So how am I doing on time? I have 10 minutes. From here, is everyone coming back after this session? I think this is actually a better point to break than to jump into this material here. So
You're cutting 10 minutes off for the second half.
I'm cutting 10. Please come back early. I am going to use the full material. But you don't want to cut off in the middle of this, and I don't want to hold you past. This part takes a little bit of brain power, especially if you're not familiar with the C++ notion of sphinai. Previous presentation of this material has said I need to take a detour and teach people the mechanics of sphinai at this point. And there's a whole bunch of fun stuff in C++11 we can detour into that makes this much easier. So please back in an hour, in 10 minutes.